Welcome back. If you remember earlier, we built and visualized a decision tree for predicting diabetes. Now we'll evaluate how well it performs and look at ways to prevent overfitting, which is a common issue with decision trees. Let's begin by evaluating how well our model performs. We'll initialize and train our decision tree model again so that we aren't reducing max depth, make predictions on our test set, and get the performance metrics. Our model has achieved an accuracy of about 95%. While this looks impressive, very high accuracy can sometimes be a warning sign of overfitting, especially with decision trees. To get a more detailed view of our model's performance, let's examine the confusion matrix and classification report. The confusion matrix shows us the number of true positives, true negatives, and false negatives. This gives us a more nuanced understanding of our model's performance beyond just accuracy. The classification report gives us precision, recall, F1 score for each class. These metrics are really important when classes are imbalanced, as often is the case for medical diagnosis. Now we can also create a confusion matrix visualization to get a better idea of how our model is behaving. Visualizing the confusion matrix makes it easier to interpret. The color intensity corresponds to the number of predictions in each category, with the actual counts displayed in each cell. Decision trees are prone to overfitting, especially when they grow too deep and capture noise in the training data. The depth of our tree is 34, and it has 3,277 leaves. Our tree has a significant depth and many leaves, suggesting it might be overfitting the training data. Let's implement pruning to reduce the complexity of our model. Here, we're creating a new decision tree with a maximum depth of 3. This constrains the model to learn only the most important patterns in the data. The pruned model has an accuracy of 95%, which is even better than our original model. Let's look at the confusion matrix and classification report for our pruned model to see if there are any meaningful differences in performance. Looking at the confusion matrix and classification report, we have perfect precision for the diabetes class, 1.0. However, recall for diabetes decreased to 67%. Overall, the model is more conservative in predicting diabetes with no false positives, but more false negatives. This plot shows us how accuracy changes with different tree depths. The point where testing accuracy plateaus or starts to decrease indicates the optimal depth. This happens around a depth of 2. We're looking for the simplest model that achieves good performance on unseen data. So let's visualize the original complex tree to see its structure in detail. This is our original complex tree with no depth constraint. As you can see, it's quite intricate with many nodes and branches, making it difficult to interpret. Now let's look at our pruned decision tree with a maximum depth of 3. This tree is much more simple and easier to interpret while maintaining similar performance to the complex model. Another valuable aspect of decision trees is feature importance, which tells us which features had the greatest impact on the model's decisions. Let's compare feature importance between our complex and pruned models. These plots show the relative importance of each feature in our dataset. Notice how the most important features are similar between the two models, which suggests that our pruning hasn't fundamentally changed what the model considers important. In the pruned model, HbA1c level is by far the most important feature at 66.4%. Blood glucose level is second at 32.35%. Age contributes 1.25%. Other features have minimal contribution. This aligns with medical knowledge that HbA1c and blood glucose levels are key indicators for diabetes diagnosis. Okay, so we've seen the decision trees are powerful and easy to interpret, but they can overfit if not tuned properly. This wraps up our demo on decision trees. Now you know how to build, tune, and interpret them effectively.